All right, in this last video for this week, what we're going to do is talk a little bit about permanent magnets. So we've already built up this idea that moving charges cause magnetic fields, and that currents can cause magnetic fields. And so the question before us is, well, magnets, how do they actually work, right? Where's the current in this situation? And so we have to go back to an atomic model that we know to be incorrect, but it helps us understand where this could possibly come from. Okay? So if we think about a positively charged nucleus, and we think about an electron whizzing around that positively charged nucleus in a circular orbit, that helps us understand that there is a charge and it is moving, right? It is a little loop of current that can produce a magnetic field, a very little magnetic field that is associated with each atom. Now, this is a bad model. This is not actually how electrons work, right? It actually takes us some understanding of quantum mechanics to really be able to generate the theory of magnetism that is grounded in what we understand atoms to actually do. But it's one that sort of helps us understand, sort of classically, what's going on with magnets, like physical magnets, like your refrigerator magnets, for example. So if you imagine a bunch of these little loops of current, each one of them produces a magnetic field. And if we use our sort of right-hand rule situation, what we're going to find is that for each loop of current that goes around like this, we produce at the center here a magnetic field that points out of the board. And so if you imagine a bunch of electrons that are in this sort of lattice of matter, right, and they're all sort of next to each other, if they all happen to line up like this, they all generate little magnetic fields that superpose, right? They all sort of add up to give you a combined magnetic field associated with each of the atoms that's actually in the lattice. Now, the problem is that if this were true across very large domains, like if it were true in this piece of chalk, then everything that we have should be magnetized. And it's not. There are only certain kinds of materials that are magnetic. And so the question is, well, how does this happen? And the answer is it's a very interesting material science problem that's associated with a model of what we call magnetic domains. Namely that for most materials, these little atomic models actually are not oriented in the same direction. So they don't produce sort of a coherent magnetic field, or what we would refer to as a magnetic dipole moment, one that adds up over long distances. So this is a sort of crude picture of a piece of material, and so there might be like one of these guys that produces a magnetic dipole moment or a little magnetic field that points in this direction, and the one right next to it might point in the opposite direction. And there might be one over here that points like this, and one that points down, and one that points up, and one that points over here and over there, and so forth and so forth. So that essentially when you look over a long distance, like a macroscopic distance, like this chalk, being about 2 or 3 centimeters long, there's no coherence. There's no collection of material that has a magnetic domain that is that big. On the other hand, there are different kinds of materials that have some longer coherence, that is, over some longer distance, they have a collection of atoms that kind of all give you magnetic fields, or in our case here, magnetic dipole moments that all point in the same direction. So for example, there might be a region here that all of them line up like this. And then there may be some region over here where they all kind of line up like that. There may be some region here where they all kind of line up like that, and so forth and so forth. So we can think of like, a wide sort of variety of these guys. And over some longer distance, right, so maybe a third of the chalk or half of the chalk or whatever, there is some collection of atoms that all kind of point in the same direction. These things we refer to as magnetic domains. And how coherent they are, sort of how, over what distance you can get them to sort of all line up, how big they are, really determines sort of the magnetic properties of the material that you're looking at. So in this case, we kind of have everybody sort of pointing to the right. Some point up, some point down. And so in general, there might be some sort of north pole on the right-hand side and south pole on the left-hand side. But it's probably a weak magnet in this case. Whereas in a really strong magnet, what you would tend to see is maybe a lot of coherence. So everybody lines up over very long distances. So this might be a strong magnet. Right? And the difference between the two is really at the macroscopic level, right? The thing that you observe is how strong the magnet is in picking up stuff or attaching itself to other magnetic materials. But it's a result of the coherence of these microscopic states. That is, or the submicroscopic states, rather, these ideas of having atoms that produce a very, very small magnetic field that add up over a very long domain. And so the difference between no magnetization, weak magnetization, and strong magnetization are all a result of basically how well aligned these things are. So that's one model for how permanent magnets work. It's a classical model. It uses this idea that we know to be wrong, this loop of current, but it does give us sort of qualitatively what we would expect to see, that there are some materials for which there are no magnetic interactions, and there's other ones that have very strong ones. And it relies on this idea of the magnetic domain.